Uh, so I will talk about the high-level overview of computing resources at SDSC. Not necessarily focusing on data-intensive computing, although you will see glimpse of that. And this is obviously involved many researchers and staff from SDSC. Some of them are here: Marty Candice, Subha Sivanyanam, Hai Sankai, who is our storage system expert. So just a very high level, SDSC's mission is translating innovation into practice. So basically use cyber infrastructure to solve scientific and societal and industry problem. And I will talk about some of the machines that we have at SDSC. Expanse is our NSF-funded workhorse machine. Voyager is an innovative AI architecture built with Habana's Gaudi and first-generation inference processors. Triton is a shared cluster, is a condo cluster, like they talked about the University of Florida, which has the DDN solution. And National Research Platform is innovative architecture. I'll talk about some of these machines, not all of them. So the Expanse machine is a AMD processor and NVIDIA GPU-based machine that's about, when it initially started, about 5 petaflop, and I'll talk about the next slide. A few other racks were added. Now it's up to 6 petaflop, and it has the idea is the long tail of science. So have thousands of users do all kind of science from every domain science and social science as possible, instead of 1 or 2 users taking up the whole machine. It has some innovative feature of composable system. We have demonstrated cloud bursting to AWS clouds. User can submit job to the batch scheduler to Expanse, and skipping all the details, AWS node in the wherever it is may appear as an additional node to the user. He or she can tag a flag on the scheduler, and that job will run on the AWS cloud, obviously with all the image and file transfer and all of this. So it's obviously NSF funded machine. It has 728 2-socket AMD ROM nodes and 52 4-way GPU nodes. And then I was mentioning recently NSF has given us award under this PATH program. So for that one, we have 2 other racks, but with advanced Milan processors and A100 and SDSC. Ourselves, we purchased a rack so that we can sell cycle to industries and make money. So Expanse is designed, as I said, with the productive computing for the long tail of science. It has 13 what we call SDSC scalable compute units, and each one of them have 56 CPUs and 4 GPU nodes, and the 3:1. So there is a non-blocking network within within a rack, and then 3:1. If you look at the numbers, there is let's see. 60, 100 HDR, and then 10x 200 HDR going up to the Lift2 switch. It's a liquid cooling, and we have 12 petabyte cluster and 1 petabyte whole system, and 7 petabyte of Ceph. So again, our focus is have a lot of scientists, graduate students do science instead of just few of them taking up the whole machine. There are other kinds of machines, both at NSF and DOE for that. So a lot of training, outreach activities at various venues. And you already heard about the Open On Demand, which allows a GUI-based access to use supercomputers, hides the complexities of file system and batch script and all of those, provide Jupyter notebooks. We have a program for HPC at MSI where for all of these NSF awarded supercomputers, there is a 10% discretionary time that a director can give out to anyone, the PI of the machine. So we have decided part of that will be given out to the MSI institution, so they can very quickly get to learn HPC, and then the majority of the machine is allocated to the access program, just like many other NSF-funded supercomputers are. Now we'll talk briefly about the Voyager machine. This is another NSF award for innovative architecture. And we decided to, with the title of Exploring AI Processors in Science and Engineering, we decided to make a supercomputer which is built with AI-focused hardware. So that's the key word. It's not a general-purpose machine. It's not GPUs where you will do excellent AI and general-purpose computing. We wanted to explore, and because NSF allows in this particular category to be little risky, little innovative, and not have a production-ready machine where a lot of science getting done, just like what in the Expanse machine. Here we can have new software, new model that are being developed when we work with a select user community, one-on-one work, explore this new AI architecture to see how good it is, what are the characteristics it has compared to general purpose GPUs, which are also excellent for AI. So we have, so this is, right now it's working only on TensorFlow and PyTorch, although custom applications are also possible. Whoever is super expert can do that. Our initial work for the first 3 years will be primarily with TensorFlow and PyTorch implementation only for deep neural networks. It's a very specific AI-focused hardware, not a general purpose machine at all. And even with Habana, which is Intel acquired company now, they are developing new models. So primarily it's vision and natural language processing. So as we select scientists from all domain sciences, we have a meeting with them to figure out, is that the right model to explore all the characteristics of this machine? Without going too much in the detail, they have specific training processors and specific inference processors. So it's very specific, not only deep neural network, not only TensorFlow and PyTorch, although there are custom coding possible, but it's they're a separate processor for training and their first generation inference processor. And we have 42 training nodes, each with 8 cores, so 336, and similarly 2 inference processor, each with 8. And we have a 2 petabyte of Ceph file system, but we might be, given its innovative architecture, we can explore a lot of things. We have a lot of flexibility. NSF has given us that flexibility. Okay, you can do it with Ceph, see how does AI models do, maybe switch it to Lustre, see how does AI models do. So we have the flexibility which you don't have with other machines like the Expanse. It has to be workhorse, production, everything working, software stack, stable from the day one. We are going too much in the detail. I will mention a little bit about the innovative architecture because we are very interested to explore the scale-out training. But anyway, going back to the Gaudi training processor, it has 8 tensor processing cores, each with 100 gigabit Rocky ports. So here's the key thing: there is no proprietary network. So that's the key thing. So you can use Ethernet-based network. So we have a Arista switch. The way these Gaudi processors work, there are 8 chips. Each has 100 gigabit ports. 7 from each one of these 8 is going to the other 7. So all-to-all non-blocking connection between all the 8 chips in a card. And then there is 100 gigabit that's left. So there are 8 cards, 8 times 3, 2400 is scaling out to Arista switch to other nodes. So this is something we are very eager to explore. How does a large model using this architecture and scaling out works? There is the first generation inference processor and the Synapse AI library. It has its graph compilers. So it hides the lower level optimization needed for this new architecture of Gaudi and Goya. You implement in TensorFlow and PyTorch, which is very quite popular. And then there, Habana's whole software stack will take care of taking hopefully the advantage of the architecture. So that's what we want to explore with the community. Here's a list of all kind of domain science applications in AI. As you can see, pretty much all are TensorFlow and PyTorch from wide areas of domain sciences in training and inference that we are exploring on this machine. And there are many other applications. I'll quickly go through some. Here's a cardiac image analysis. This is Mai Guen. I'm the PI of the Voyager project. Mai is one of the co-PI. So they are using cardiac image data when it's done manually. Obviously, you can imagine if this can be take advantage of AI, that will be great. This code has successfully ported to the training nodes, and I think now she is working on the porting to the inference part also. And this uses a UNet architecture. The second one is a data-driven numerical weather prediction using deep learning. These 2 researchers from Argonne National Lab. I think Amit Malik, I think he has a faculty position at Penn State also. Again, basically trying to use deep learning to do high resolution weather prediction 14 days out instead of doing rigorous mathematical, as you know how they do the weather prediction. Again, this is a UNet architecture. Their code has also been ported and running on the machine. This researcher, Ziaze, his interest is in ultrasound computed tomography, is applied in various fields, structural health monitoring and non-destructive evaluation, etc. And this code also is important to the Gaudi training nodes, and for the inference one, we converted it to this Onyx model, and through that is running on the inference processor, also a unit architecture. Another research group is from University of California, Irvine, Professor Mike Pritchard and his grad student Griffin Moore. They are looking at this variational autoencoder approach to capture all the very lower level microphysics that happens, and which are usually needs to be parameterized, and hence there is error. So idea is to see if the machine learning can do things fast and yet capture the lower level science. Again, very little code change was needed to run. These codes are running mostly on GPUs, so very little few line code changes were needed to run on the Habana processor. I'll talk about this is the last application. This is Voyager, is a copy of Javier Duarte. His area of research is high energy physics. He has been involved with the Large Hadron Collider for a long time, and he's applying AI algorithms to basically, as you know, the Higgs boson and things like that. When they have these particles have interaction with the detectors, they leave tracks, and they produce petabytes and petabytes of data. They try to calculate from those using Monte Carlo and other methods. Can they find the signature that it was Higgs boson interaction? Or some other particle the high energy physics people are interested in. So again, this is a graph neural network, and that has been based on the detector measurement, and it uses a TensorFlow, and again via the Onyx model. It is already out of the box. Pretty much all the operators it needed was supported, but some were not, so they worked with the Habana experts. So one thing I want to mention, giving an innovative architecture, we really need to very closely work with Habana, because they know what is the next model, what is the operator that is optimized for the architecture with the graph compiler and etc. So we work very closely with them. So, but I think what Javier told us, this is the first machine learned particle flow MLPF that was ported onto Habana processors, and they are now working on the training with CERN researchers, and they have planned for various other things. I mentioned the Condo cluster we have at UCSD. This has all the features of the Condo many of the features of the Condo that you heard from the previous speaker. It has both CPUs and NVIDIA GPUs, and this is the machine where we, I think, recently or maybe the first time have a DDN solution. So we are very happy about that, working with the DDN, and I think it will probably grow. We may have more storage from DDN. And this has all the features. Users buy nodes, and then they can, based on the scheduling system, if other nodes are not used, they can scale out just like any other Condo cluster. And we have a very good user support and extended collaboration with the community of, so this is for UCSD faculty. The other machines, Expanse and Voyager, is for the national community. So that's the difference, because those are NSF funded. This is UCSD provides user support funding, and then the faculty with the grants buy nodes and build the Condo. There are industry with whom we also have advanced user support on genomics, molecular dynamics, and web services. National Research Platform is another innovative NSF award. The PI is Frank Worthwin, who is the new director of SDSC. He's just about a year he has been SDSC director. This is distributed at in the Massachusetts Green High Performance Computing Center, University of Nebraska-Lincoln, and at SDSC. It has FPGAs, A100, A10, and so all kind of distributed innovative architectures. And it has a lot of innovative features like the Giga I/O, which that allows a rack of hardware to behave like a single node, and as well as various other features. Frank has been, through the part of Open Science Grid, which you many know, has been heavily involved in the national data infrastructure, and I will not read all of them, but like distributed caches across many places in the country, so that any university or campus is only 500 miles away from a cache, and all kind of distributed data infrastructure using Ceph and various other multiple NSF funded project and DOE projects, so he's applying those into this. Again, this project has many science drivers and pretty big name applications, Nobel Prize winning, LIGO, IceCube, as well as many other areas of genomics, even fire prediction. Okay, so my last topic before I let you go for the drinks. So CloudBank is a NSF-funded project. What it does is any academic researcher who wants to use cloud time can request supplemental funding from NSF, and NSF sends the money to this CloudBank group. This project PI is also from SDSC. SDSC is ex-director, and then University of Wisconsin Ed. Lazowska and David Keller and Kathy Yelek from UC Berkeley are the co-PIs. So basically any academic researcher can request cloud time from any of the vendors by submitting a supplemental proposal. If the proposal is approved, then money goes to CloudBank. CloudBank buys cloud time at a good rate from all of these vendors and gives the good rate, passes it on to the academic researcher for his or her work and grad students, and there is no IDC, indirect cost. That's the way it's set up. So initially NSF started it, so the NSF issues calls for, all the NSF always has proposal calls, and when you write the proposal you have to request time, so which was good that way. NSF, many cloud awards were made, but recently NSF has opened it up so that this particular director of NSF called SIZE, any SIZE awarded PI can go and request time through this route. So it doesn't have to be for a future call. So the CloudBank is about 2 years old. They have made all $0.7 million award to various clouds, to various PIs, 100 NSF awards. So that's a very good program. I just wanted to mention that. I don't think there's any time or interest for questions, maybe.